All right, here we go. Physics reaction video number 39. I did a search today, I believe, for honors physics lecture. So here we go. All right.
Okay, day 64. Reviewing for a test is tomorrow. I'm here with my friend Madeline and Nick, but we're also joined by Cornelia, who has been given the task of writing the test. So she's writing the test for us with some of your help. You're encouraged and invited to collaborate with her, but if you guys...
So I'm not sure if that means that's a student or maybe a fellow teacher. That's interesting. I mean, certainly the idea of having students write an exam is a thing. Can be useful. It could be that it's his partners, his teaching partners at the school. I don't think there's a live audience here, just the way he's focusing on the camera. So looks like we're going to do a review, though he said that was tomorrow. And then I think this said geosynchronous satellites, so maybe some general relativity or at least some triangulation today. So that should be cool.
You guys are not part of that process. You're only hurting yourself, right? And so this is an opportunity for you to engage with content, and work with each other, and show that you understand the material. I asked these guys to dig into a satellite question, which was item 47. We are going to do a little bit of work today related to and geosynchronous satellites. We gain another person. Cornelia is joining us from the other days. Did you know Cornelia's father is works in the fortress in Oslo? Yes, he does. That's cool. Yeah. Okay, item 40.
All right, I don't know how long that break was, but I really like this. I can read this really, really well. It's so funny when I read this one. This jumps out at me. Venus orbits the sun with a period of this many seconds. Nobody cares how many seconds it is. People want to know how many years it is, or how many days it is, or how many months it is. If you put it in seconds, nobody knows what that means compared to Earth. I always remember Earth's period a year is pi times 10 million. So it must be 31 million. So 3 times 10 to the 7. So this is roughly 2 times 10 to the 7. And Venus is closer to the sun than we are. So yeah, of course, I don't need to know the mass of Venus. All that matters is where it is, Kepler's third law. So, and of course, from that, we can figure out how much closer it is. If we can remember the square roots and the cubes and all of that other stuff. But it looks like if 47 is what they're going to do, that's exactly what we're up to. But I really like this this framing. This looks great. I'm not 100% sure why this whole thing is in black and white. But let's keep going. I'm just going to back it up just one smidge. There we go. We won't do this whole video.
Yeah. Okay, item 47 is about the planet Venus and the planet known as the sun. It's not a planet, Mr. Ford, it's a star. What is the average distance between Venus and the sun? If we know the period, given as 1.94 times 10 to the 7 seconds. That's nice. They put the time period in seconds, not in days or years.
So, Kepler's third law gives us information about the main axis of the ellipse. I think roughly the way it's usually stated, it's half of that, right? And if it's a circle, then it's just the radius of the circle. What I'm trying to decide is, can you get to the average distance from that? If you know the semi-major axis of an ellipse, do you know the average distance? I actually don't think you do. Of course, we're sort of spoiled that in our solar system, all of our planets are their orbits are pretty dang circular. So my guess is they're just going to go for the semi-major axis of the ellipse here using Kepler's third law, but I'm curious to see what they do with that word average.
For us. Thank you for doing that. So what are you going to do with that, Nick?
We're going to plug it into the equation.
An equation? Do we know an equation, a relationship that'll be useful?
Kepler's third law equation.
Kepler's third law is a good relationship here.
So it does seem like there are some students in the room, which is super interesting. And he said, what are you going to do? Well, we're plug it into some equations. And I really loved the reaction of, well, okay, let's go back and see what are the relationships that we know.
It says the time period is equal to 2 pi, 2 times pi. And that's it. No. Divided by the square root of universal gravitational constant times mass of the planet sun. All of that freaking thing times the radius raised to the 3/2 power, right? Ta-da! Ta-da! Oh my god, this is terrible.
Okay, yeah. Oh man, Kepler's third law just drives me crazy. It just seems to come out of nowhere. You know, who cares about the 2 pi? For the moment, let's forget about the square roots and the 3/2. Um, is it really a square root and 3/2? Oh, it's just r is raised to the 3/2 power. Okay. So from this, I see that if the mass of the sun is bigger, the time is shorter. Yep, it seems to me that if the mass is bigger, it's pulling it harder and it's go around faster. Basically, a better way to say it is to go around in the circle. You'd have to be going a lot faster to avoid being pulled into the star. The fact that r is in the numerator, the further out you are, the longer it should take to go around. Yeah, I guess that makes sense.
So what is the mass of the sun? No. 6.67 is your universal gravitational constant. Luckily, the book has done some examples previously with the
I love
mass of
this.
the sun. And so we just got to flip back until we find it. Or we can go to the data tables at the end of the book. Or we can just look it up online.
Oh, I love that. Or you could look it up
Mass
online.
of sun. Mass of sun in kilograms.
That's just not that far back.
I can't believe it's not there.
Talk about the sun. They're saying they have a version of helium that's not like ours are. That's kind of weird.
Is it an isotope of helium?
Well, yeah.
So I really like this, right? So what he's doing is he's saying, well, we need the mass of the sun. What the heck is it? It's not something that people tend to have memorized. I seem to remember something about it's 100 times the mass of the Earth. Could that be right? I'm not sure if that's even right, but I don't know the mass of the Earth. So could I get there from the fact that it's 9.8 on the surface of the Earth? Yeah, because I happen to know the radius of the Earth is 4,000 miles. So I guess I could get to what the mass of the Earth is. Ooh, I'd have to know what G is. I don't remember what G is either. Huh. But, yeah, I'm trying to figure out whether I could figure out the mass of the sun if I was stranded on a desert island. I'm not sure. 93 million miles is how far away we are from the sun. That's just a number I seem to happen to know. So if I know how far away I am, if I knew Kepler's third law, because I know that the period of the Earth is 1 year, I guess I could get the product of G times M, right? G times the mass of the sun. That product I could get from that. Interesting. But anyways, I really like that he said, like, I don't know what it is. Let's just look through the book here. And he gave 3 ways you could find it. Flip through. It's probably in a recent example. Go to the, I don't know, back of the book or front of the book and find it. Or, use the internet, right? Like just say, hey, Google, what's the mass of the, let me try that. Hey, Google, what's the mass of the sun? It's not listening to me right now.
Here are some details.
2.0 times 10 to the 30 kilograms. Oh my God, that's huge. All right, let's keep going. Actually, the math.
Well, in addition to knowing that number, we need to rearrange this and solve for the variable that they want us to solve for. What is the variable that they want us to solve for?
R.
R. Radius.
So it's interesting, right? That the book, you saw that same exact equation in the book that had that r in it, right? That's the semi-major axis. So it seems like what the book is saying, oh, good Lord, they're all circular. Let's just run with it. But then in the statement of the problem, it actually says, what is the average distance? The semi-major axis can't possibly be the average distance. And what do you mean by average? Do you mean average over time or average over, I guess average over time? Huh, that's interesting. All right, just a little bit more here.
Okay. So to do that, we need to isolate R by itself. And what I would do is multiply the time period by the inverse. So instead of putting the numbers in and plugging and chugging, let's go ahead and rearrange the symbols.
Love it. Ooh, that erased amazingly
Right,
well.
Madeline? That would be
I love how
t
he's
times
involving the students, right, Madeline?
2 pi on the bottom. The square root of g mass sum.
All right, so when do we think that the framing of the camera is going to be fixed? My guess, never, right? Because my guess is he set this up and he's done this a whole bunch of times, and it's always worked for him. And that for some reason he's using a portion of the board now that he doesn't usually use. Right? Is there anyone watching this stream live say, I can't see, I can't see? Will the students in the room think, wait a minute, you're using a portion of the board that we can't see? I mean, and of course, all people really want to know is the answer. So they might not care as long as he goes low enough for them to see. So I'm really curious to watch that.
On top, right? All of that equal to radius raised to the 3/2 power.
There is a fair amount of noise in the background. I'm not 100% sure how many students are here. This may literally be video for just those who are quarantined at home. But the fact that he works so hard to get the card framed in the camera and the textbook framed in the camera, I wonder if that, when he does that document camera, I wonder if that's projected on the screen. But I'll bet you anything, what he's doing now, is not on the screen in the room. I'll bet you this is not being projected into the room. So this is tough, right? Like, how often do you have to check your framing? Now he's talking a lot, so maybe you just don't need to see it. This is really interesting.
So 2/3 power of the equation.
So
Ooh, I like that.
will that be what we do here?
Aren't you supposed to divide the other thing?
Ooh, using his hand.
On our side, you're supposed to divide the square root b and s. Right?
Well, I did the opposite of it to cancel it from this side of the formula and put it on the other.
So this is really, really fascinating, and I'm watching his face and I'm listening to his voice, right? One of two things is happening right now. Either he is a little stumped because he's approaching this problem in a slightly different way than he's used to. I don't think that's the case. Or he's really trying to put his mind into the mind of a student, like, man, this is an ugly equation. We need to somehow get R isolated. Boy, but it's in this equation in a funky way. So a student said, let's raise it to the 2/3 power. Awesome. Super useful. But he didn't do it right away. Either he doesn't know, in which case this is a great performance a great thing for the students to watch, because I am not at all worried that he's not going to figure it out. But I don't think that's the case. I actually think he totally knows what he's doing, but he's doing such a great job of making sure that every student can follow, like, boy, this is tough. We need to isolate this R.
Other side.
Oh, yeah. Never mind.
Okay. However, what do I do with that 3/2?
You got 2/3 it.
You got to 2/3 it. It's a verb.
So I can write it like this.
Where's the t?
I forgot the t. Okay, so no, that goes on the inside. You're right. Times t.
Oh, I like that.
Okay, I can even
Catching
put
that?
on there, right there. All that is equal to radius. That is an ugly little arrangement, isn't it?
No question. I wonder if the units are easy to figure out.
That's not nice, Mr. Ford. However, we can put that into the Web 2.0 calc or any calculator that you are used to using.
Okay, so here he is reframing. So now we can see that, and he's encouraging people to dump it into a calculator somewhere. This is such an interesting expression. Can we figure out what the units need to be? So we know that GMM over R squared is newtons. So GM, that's tough. And then the square root. Oh, man, it's ugly. How can we be convinced that this is going to end up being, how can we be convinced that this is going to end up being meters? The square root here, it gets canceled by the squared, but then we cube root the whole thing. I mean, I'm sure it works. I'm just pointing out that the struggle that students might have is, whoa, this comes out of nowhere. How could the units possibly work? I don't understand what the cube root of a meter is or the cube root of a second is. That doesn't make any sense to me. And yet, apparently, this is all going to work out to end up being meters. And that's my struggle with Kepler's third law, is it's just so nasty. But let's see, in this case, they're going to get some radius of Venus. And I mean, frankly, for me, all I know is it's less than 93 million miles. That's all I know. Something less than 93 million miles. So I'll take a guess. How about Mercury, Venus, Earth? So 80 million miles? I'll guess 80 million miles.
Okay, I'm
Ooh,
hanging out with
cool.
my Web 2.0 calculator.
Cool.
I did 2 open parentheses and I hit the square root
Love it.
of G, which in this case is going to be 6.67, 10 to the negative 11. Did you remember that?
Oh, nice.
Sweet. We're also going to multiply.
So a tiny little problem that I have with online calculators, and this one seems awesome. This button is missing on many, many, many online calculators and smartphone calculators. This times 10 to the button, right? And it's nice because, well, I'm not sure how this calculator works, but most calculators now treat this entire thing as a single entity. So for example, if you did 1 divided by this whole thing, it would work correctly, as opposed to literally typing times 10 to the, right? So times and then 10. Well, they've got this too. Yeah, so times this and then negative 11. I hate it, but it looks like this calculator has that times 10 to this. So let's just take them back a little bit.
You remember that? Sweet. We're also going to multiply that by mass of the sun, which my friend Nick over there pointed out is 1.99 times 10 to the 30th.
30th.
Is that in units of kilograms?
Ooh, love that check.
Okay, all of that is going to be, I close parentheses and I'm going to divide by 2 pi. And I'm going to say 2 pi, because that's what I do.
Multiply the top by t.
So right here, I don't know how this
now or
don't know how this calculator works, right? But a lot of calculators, we need another slash right here. I'm not sure if it realizes that it needs to put 2 pi in the denominator or not. Let's see, if this is wrong, basically this will be 10 times too big, but that's inside of a raised to the 2/3 power. It's going to be 7 times too big. So this might take it over 93 million miles. So let's keep an eye out for that.
I could do it later. So let's go ahead and do it now. Just know that it's not in the square root portion. So we're not going to square root t. And the t is how many seconds? 10 to the what?
Oh, this is an awesome calculator. Look at the up above here. It should be clear to him that pi is not down here. Oh, I love the fact that it sort of reformats it for you. I wish it was framed better in the screen. What did he say this was? Calc 2.0 or something like that? Very cool.
7 seconds. Boy, this is a heck of a question, isn't it? Divided by 2 pi. Okay, so I have all that stuff inside brackets, except for this 2 pi needs to be a dividing thing.
Aha, so we fixed that. So now that should put a pi up here. Yep, it does. Nice. Now he has to raise the whole thing to the 2/3 power.
All right, and
I guess that's
raise
this
it to
button.
2/3, huh?
Or it could be this button and this button.
So I could do it like
Both of these
this.
buttons. Awesome. Awesome. That looks right to me now.
Wow, wow, wow. That'll do, right? That'll do, pig.
Love it. I love this read.
If you wanted to talk about units, you knew that.
I love this reformatting that the calculator does because this reads a lot better than this does, right? Now the students have to type it in this way, but it looks nice here. Now, right, there are some pieces of software. Mathematica is number one in my mind that literally when you type it, it starts to look like this. You would hit Control 2, gives you a radical. Then you start typing things. and the radical just extends, and then you get out of the radical and you keep putting times in there, and then when you hit control slash, it literally makes a fraction for you, and right, so it looks super nice. But this looks great. I can't quite see the fraction symbol in the up here, but I think it's looking really, really great. So let's hope that it ends up being what did I say, 80 million miles. I want to take that back. I want to say 70 million miles.
This was in kilograms, no, newtons times meter squared, kilograms squared per meter squared.
No, meter squared per kilogram squared.
Yeah, because the meter's squared on bottom, but we take, oh God, units here are going to be super ugly.
Ooh, I was wrong.
It should end with meters, so we're looking for radius.
Oh shoot,
So
I was
it's
saying miles.
0.08 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1.98, 10. Okay. So let's ask the Google tubes.
I'll see if my phone is faster. Hey Google, what is the radius of Venus? Oh, that's not what I wanted.
1.08.
Hey
Then
Google,
there it is
what
right
is the orbital radius of
So
Venus?
our work agreed with what the internet says. Oh wait, that's kilometers though, but this is 1, 2, 3, 4, 5, 6, 7, 8, and we had ours to the 11th, right?
They got it in astronomical units. 0.7 it said, so that's 70% of the Earth's
Good news
radius.
bears. At the top page 331, it shows a GPS satellite being released from.
All right, so I'm just going to stop right there. Lots and lots of really interesting things. Let me just go back far enough to see. Where's this working? There we go. Come on. Back. I love this. The work here was really great. I just loved how he pointed out how ugly and nasty it was. I liked the multiple camera stuff. I really liked how he was involving the students in the room. So this was really, really interesting. Calc 2.0, check it out. It looks like it reformats your students' equations. I loved that. Lots of good things here. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.